everyone, this is Han Jen and your instructor in this class. In this video, I'm going to talk about how to design a tension member. And in this video, we're going to talk about what are the tension member and its connecting elements. So how to define the tension members, and we're going to talk about the limit states we have to consider in determining tension member capacity. And we're going to define the shear lag effect, and in the end of this video I'm going to show you how to determine the tension capacity for a plate with staggered holes. And that being said, in this video we mainly focus on the yielding and fracture limit states. Okay. And alright, define a tension member. Obviously, a tension member is something that carries tension only. So, you know, there's no moment in it, only tension. Okay. For example, the tension member, typical tension member is the truss member, bracing, hangers, and the cables. And also, don't forget that those members connecting elements like gusset plates, splice plates also should be considered as a tension member. Okay, so in this picture, I'm going to show you some examples, right? So, and this the bottom cord is an tension member, right? So the bottom cord is carrying the tension only. And we'll see on the knot, there's the gusset plate connecting the diagonals tension member, vertical member, and the bottom cord. And in here, there's the splice plate. There's some splice plates connecting the two lateral cords together. Okay, this is a very famous example. So the initiate event in the collapse of I-35 West Bridge in Twin City, Minneapolis, is due to the failure of tension members and is a gusset plate. Okay. So the initiate event in this collapse is the failure of the top end, upper end of this diagonals and member, and later on the failure of is connecting gusset plate at the knot U10. Okay. And the tension member in this bridge had inadequate capacity even in the original as designed condition. So in the day of the collapse, this bridge was underwent a roadway construction. So like 2 hours 15 minutes before the collapse, there were equipment and aggregates stockpiled in the middle span of the bridge, very close to the critical cross-section of the bridge. That worsened the situation and eventually led to the collapse. Okay, so as you can see, those pictures are from the annual inspection report. So especially the one on the upper right, showing that the gusset plate already bowed even before the collapse, show you a sign of yielding, right? So that's a sign of yielding, meaning that the gusset plate already yielded even before the collapse. Okay, and this is a sketch of the splice plate, right? So oftentimes we have to splice it because of the transportation capacities, right? You couldn't transport a very long element to the site, so you have to splice it on site, connecting them into one unit. So when the tension applied on the member, and maybe it may be fail within the member or fail within the splice plate, right? Okay. So the tension member and its connecting element forces, can we analyze both at the same time? So for example, in this unit, we have to analyze the tension capacity for the gusset plate as well as the tension member, right? They all are in tension, so we have to make sure both of the tension member and the gusset plate are adequate to resist the expected load. Okay, so how can this member fail? Well, there are 4 limit states in tension members we have to consider. Note that tension members has the most limit states to check compared to the beam and the columns, right? So actually we have more work to check the design adequacy for tension members. So in tension member, we have to check the yielding limit state, fracture limit state, bearing or tail out, and the block shear. Okay. In the corresponding sections already marked out here, right? So the tension member, yielding and fracture is described in the manual section D2. Okay, and tail out and block shear actually described in the chapter J. Chapter J is for the connections, right? So these 2 limit states actually are described in chapter J, connections. Okay, so first of all, let's talk about the first limit state, yielding. That is the most straightforward one. Yielding occurs away from the connection, meaning that the yielding occurs in between the members. Okay, and Pn, the capacity for yielding is equal to Fy times Ag. Fy is the yield stress and Ag is the gross cross-sectional area. So meaning that this limit state occurred actually in the member, within the member. Okay, so that's why we use the gross cross-sectional area. And note that phi we call the resistant factor. Okay, so resistant factor. Resistance factor for yield limit state is 0.9. It's 0.9. It's pretty high. Okay, that means we have more confidence in determining the yielding strength for the member. So we apply a higher resistance factor. And why I say that? Because yielding takes place due to the excessive elongation, like showing in the sketch here, right? So that actually gives you a warning of failure, right? So if a member is going to fail due to yielding, it will show a elongation, the sign of elongation beforehand. So that way you got the warning and you know that the yield failure is going to occur, then engineers will replace the member. So the engineers may know that it's the time to replace this member with a stronger one, with a bigger AG, right? And then collapse will be prevented. Okay. The second limit state is the tension member fracture or rupture. So they mean the same, fracture or rupture. Fracture or rupture usually take place along the holes along the holes. Okay, so in this case, Pn, the capacity, equals to Fu times Ae. Fu is the ultimate tensile stress, and Ae is the effective net area. So that's going to be the total area deducted by the whole areas. And in this limit state, as you can see, that you're going to have a different resistance factor. The resistance factor for fracture is equal to 0.75. Right. So in fracture limit state, you have to apply a lower resistance factor, 0.75. That's because fracture is more critical than yielding. And most importantly, usually fracture occurs without any warnings. It's a sudden failure, it's a sudden fracture. So it's more critical than yielding, and we have less confidence level in fracture failure than yielding failure. So that's why we have to apply a lower resistance factor. So meaning that we learn the reliability factor beta, right? So meaning that the failure probability is higher in fracture than rupture. Okay, so that's pretty typical. Usually we apply 0.9 of resistance factor of 0.9 to yielding failure, and 0.75 for fracture failure. Okay, so that's pretty common. Okay, now you're gonna ask me a question, how to determine the effective area. So let me move this icon to the top. Okay, so now comes with the question, how to determine the effective net area. Right, well, in the menu, page 16.1-29, equation D3-1 gives you the equation of net area AE. So AE equals AN times U, and AN is the net area, and U is defined as shear lag factor. Okay, so we leave the U shear lag factor in a few minutes. I'm going to talk about it in a few minutes. So first, how to determine the net area is pretty straightforward, right? So it is the gross area subtracted by the area removed by the hole, subtracted by the area removed by the holes that intersect the net rupture surface. So which is the gross area subtracted by the whole areas. Okay, so for example, in this scenario, AN gonna be the gross sectional area, which is the blue shaded area, the L angle. The blue shaded area is the gross cross-sectional area. You can find it from the menu, table 1-1, right? And there are two holes. Two holes need to be deducted from the gross cross-sectional area. So that's going to be 2 holes times the diameter of the hole and times the thickness of the angle. So we're assuming the thickness of the angle is the same for both legs. Okay, and now here comes the question how to determine the hole size. Okay, so based off the menu, the hole is equal to the diameter of the hole is equal to the diameter of the bolt plus 1/16 plus another 1/16. Okay, so the first portion D bolt plus 1/16 is the nominal hole diameter. And another 1/16 is the damage allowance. Okay, and add them together, d bolt plus 1/8. So this is for the diameter less than 1 inch. Okay, so if the diameter of the bolt is greater than 1 inch, then the nominal hole diameter is d bolt plus 1/8. Okay, and also typically, so for the bolt diameter that less than 1 inch, the nominal hole diameter is d bolt plus 1/16, and the d hole is d bolt plus 1/8. And for the bolt diameter greater or equal to 1 inch, the nominal hole diameter is d bolt plus 1/8, and the diameter of the hole equals d bolt plus 3/16. Okay, and in the page 16.1-130 in the manual, so page 16.1, so if you turn to page 16.1-130, you will find this table. And this table gives you the nominal hole dimensions of the inches. So you can see here that for the bolt diameter less than 1 inch, the standard hole, your nominal hole dimensions is the d bolt plus 1/16, right? And for the bolt diameters greater or equal to 1 inch is equal to db plus 1/8. Okay, for standard holes only. Okay, and oversized holes have different hole dimensions. All right. Okay, now that covers how to determine the net area AN, right? And now comes up with the shear lag factor, because we are going to determine shear lag factor U. Okay. Shear lag factor occurs when the element is partially connected. Okay, is partially connected means some elements of the cross section are not connected. So, for example, this is a I shape, right? The tension member is an I shape. So, for example, the cross section is a I. Right, is the two I shapes are connected on their webs. So it seems, let me use another color. Okay, so they are connected on the web with the splice plates. Okay, two bolts. Right, so it's like that. So the members are connected on their webs, not on the flanges. So the flanges, top and the bottom flange, are not connected. So something like that. So means that means in these scenarios, some portion of the member are not stressed, while other portion closer to the connections are overstressed. Okay, so meaning the blue shaded area is not stressed at all. Meanwhile, the area closer to the connections are overstressed. Okay, then so that means the actual stressed AE, the effective area, gives you the stressed area. It's the actual stressed area. right? So that's why it's called effective error, right? Meaning that in that scenario, the effective stress error is even less than net error, right? It's even less than net error. Okay, and the farther away from the connection, the fully stressed the cross section is, right? So for a cross section far away from the connection, is fully stressed, right? But for the cross section closer to the connection, is not fully stressed. So a shear lag factor U would apply. U applies. Okay, so the U account for shear lag. So shear lag means it takes a while, right? So the error when for a partially connected member, when it's very close to the connections, the cross section is not fully stressed, right? So you have, and when it comes to a place far away from the connection, then it becomes fully stressed. So U accounts for that effect. U accounts for, as you know, the swiping lines. The area covered by, enclosed by the swiping lines means the stressed area, right? So the other areas are not stressed. So here, for example, in here, the flange is not stressed. So in this area, so your effective stress will be less than the net area. So that's why U is usually less than 1. So it's in between 0 and 1. Okay, so which would have more shear lag effect? So more shear lag effect means a smaller U factor, right? So say we have a shorter connection and a longer connection, right? So if we want to draw the stressed area, right? So the enclosed area within the area swept by the shear lag stress lines is the stressed area, right? So you will see that a shorter connection length cause more of the rupture area fall out of more net rupture area fall outside of the stressed area. So means in the shorter connection will have more unstressed area, right? Will have more unstressed area. So as you can see here, right? So for example, say in here, so we have more unstressed area, and the bigger and the longer connections will cause more stressed area, right? So means the shorter connections will have smaller U value, and the bigger and the longer connections will yield the bigger U value. And in another word, longer connections will help spread the stress more efficiently. Means in the longer connections, the cross sections will be stressed more evenly than the shorter connections, right? Okay, and we examine the locations of the connections. Okay. So as the connections move further from the centroid, so one is located. So this one, the bottom picture shows the connections is closer to the centroid, and the topper one moves further away from the centroid. As you can see that in the centroid, we will have more stressed area than this one, right? So as we move further from the centroid, more area will be left unstressed. More area will be left unstressed. So this one will have smaller U, and if you place the connection along the centroid, you will have a bigger value. Bigger U value means it's more efficient to resist the tension. So that's why when you design the connection member, it is more preferable to place the connection line around the centroid line. Okay, and then this examines the numbers of the connections. So in the first picture, in the picture on the top, shows you that this angle is connected on both legs. This angle is connected on both legs, means all its elements are connected. So meaning that in this case, we'll see that almost all the net areas are fall within the stressed zone. So meaning that it's more efficient to resist the tension members. So meanwhile, if I only have one row of connection, or it's only connected in one leg, then the other leg will be left unstressed, right? So in this case, if all the elements of the member are connected, we can consider U just equal to 1, right? So we can consider there's no shear lag in this case, right? So if only one part of the element are connected, or there's no one other element were left unconnected, means there is more significant shear lag effect. So in this case, U is less than 1, approximately equal to 0.8 or 0.85, something like that. Now you will ask me, what on earth shall I calculate U? Here is the answer. Please turn to the page 16.1-30 in your menu. It gives you the table. This table provides guidance for determining shear lag factor. So the first case, all tension members where the tension load is transmitted directly to each of the cross-sectional elements by fasteners or welds, U is equal to 1. What that means? That just means all the elements are connected. So for example, you have a I shape, you have an H shape, and it's connected. All the elements are connected, means the flanges are bolted. Meanwhile, the webs are also bolted. So all the elements are connected. In this case, means U equals to 1, right? And the example will show you the double angle. So both of the angles are connected, bolted or welded. Then U is equal to 1. Other case, all tension members where the tension load is transmitted to some, but not all of the cross-sectional elements, then use this equation to determine U. Okay, U equals to 1 minus x bar over L. Okay. So x bar is equal to the distance from the centroid of the connected area to the plane of the connection. So for example, take the same example of the I shape. So let me draw it larger. Okay, so you have a W shape or I shape, and is connected on its web. Okay, now how to determine X bar? So in this case, we typically want to divide it in half. So meaning that it's equivalent that we have two channels, and this channel is connected with a plate on its web. So the X bar is the centroid of this channel to the connecting area. So the connecting area is connecting surface. Connecting surface is the interface between the plate and the channel. So that's going to be your X bar. Okay, and L is the length, the longitudinal length of the connection. So L is the longitudinal length of your connection. So that's your L. Okay, and that way you're able to determine U. And the second scenario is you have a say a wide flange shape. Okay, you have a wide flange shape, and there is a plate, either welded or bolted on the flange, right? And in this case, the connected area is the flange. Okay, so what you're gonna do? Okay, so it's a symmetrical, say it's welded on the top and the bottom. So in this case, we also want to cut it in half. So you have two teeth instead of just one H shape. You have two teeth, and the centroid is the centroid of the T. So the distance X bar is from the distance of the centroid of the T to the interface. That's your X bar. Okay. And there are some other cases in this table, so please read the description of the cases carefully to see which case it will apply to your project. All right. Okay. The number of fasteners per line in the direction of the stress. So, for example, there's 3 holes. There are 2 holes. Fastener per line in the direction. Okay, so we are 3 holes. We have 3 holes in this line and 2 holes on the bottom line. Okay. Now, so sometimes we would have scenario like this, right? We have a pattern, a fastener pattern spread out like this. We have staggered holes. So in this scenario, how to determine AN, net area? Okay. So because if you examine the potential failure paths of the plates, there might be 2 possibilities, the 2 failure possibilities, right? Say it could fail along the path of A, B, C, D, or fail along A, B, E, C, D. But which one is critical? Which one is critical? By inspection, it's hard to tell, right? Then we have to calculate it. Okay, so let's examine it by calculation. Okay, so let's look at the possible failure paths A, B, C, D. So along A, B, C, D, there are 2 holes that needs to be taken out. Okay, so 2 holes will be taken out. Okay, AB, and along A, B, E, C, D, the failure path is longer. The failure path is longer means you probably will have larger AN. So it seems like needs to be less critical. However, you have to notice that there are 3 holes need to be taken out, means you have longer failure path, but you have more holes taken out. Okay, so we have to compare the failure paths, right? So the thickness is the same. So for each failure, for the 2 failure passes, the thickness would be same. So it will be the length that determines which one will be critical. Okay, so before I jump into the AN calculation, I want to introduce the empirical rule for computing the net area along the zigzag path. So is also called S squared over 4G rule. So means that the zigzag, the length of the zigzag would be equal to okay, so the length of so AN equals the AG, gross cross-sectional area, subtracted by the whole area, D whole, times the thickness, and plus the sum of the zigzag path lengths. So that's S squared over 4G, and also times the thickness, right? So sum all the zigzag paths. So for example, along the path A, B, E, C, D, there are 2 zigzag paths. So you have to, so that's 2 times S squared over 4G. Okay. And S is the longitudinal length of the diagonal. So that's the pitch. S is the longitudinal length, and G is the transverse distance. Okay. Okay, procedure for calculating VPM based on the net area fracture. So we have to consider all the possible fracture passes and computing AN for each pass and choose the smallest AN. Okay. Now here is the example and computing VPN for this pattern, right? And note that the critical fracture path is always closer to the load applied. Okay, so in this case, the load is pulling this way. Okay, so remember the critical cross-section for fracture is always closer. It's always the one closest to applied load P. So it will not fracture over here. It will fracture along the cross-section closest to the load P. Okay, so keep that in mind, please. All right, and let's examine the failure pattern. So like I said, it probably will fail along the vertical, the straight line, along the straight line closest to P, or along the zigzag path like this, right? And in addition, let's look at this pattern to see if we will be controlling. Okay, so by inspection, it's very hard to tell which one will be controlling, so we're gonna calculate AN for each case and compare and select the smallest AN, right? The smallest the one gives smallest AN will be controlling. Okay, so the first one is pretty straightforward. We'll have the straight line, right? So your AN will be equal to the cross-sectional area subtracted by the two hole areas, right? And it tells us we have 7/8 inch bolts, and the bolt spacing is 2 inches in long direction. So let me use the green color for dimension. Okay. So 2 inches in longitudinal direction and 3 inches in transverse. Okay, so 3 inches. All right. And before that, we need to determine the hole diameter. So the hole diameter, remember, it says we have standard holes. So the hole diameter is the bolt diameter, right? So plus 1/8 inches. So it equals 7/8 plus 1/8 equals 1 inches. So the hole diameter is just 1 inches. Okay, and then AN for this scenario is the cross-sectional area AG minus sum of the hole diameter, the whole areas. So AG, it says cross-sectional area is 7.5 inch squared minus along the path, failure path, we have 2 holes, so 2 times the hole diameter 1 inch and times the thickness of the plates. The thickness of the plates is this one, 3/4 inches. Okay, and from that we got 6 inches squared. Okay, and the second scenario is like this. We have to apply the zigzag rule. So AN is equal to AG minus sum of DT and plus sum of S squared over 4G times T, right? So the cross-sectional area is 7.5 inch squared minus along the path we have 3 holes, so this time use 3 times 3 times 1 inch, which is the hole diameter, times the thickness, 3/4 inches. And don't forget, add the zigzag path, the length of the zigzag path. So the length, we have 2 zigzag paths, so it's 2 times S squared. S is 2 squared over 4 times 3, and times the thickness 3/4 inches. Okay, and what do we get? You probably will pause this video, calculate it out, and compare what I got, 5.75 inch squared. Okay, now we can see that, and this pass has a smaller AN, means this one is critical, right? Is critical compared to the yielding, to the first pass. Okay, now let's look at this one. Let's see if it could fail along this pattern, with this pattern. Okay, it's kind of different. So when this one we need to draw the free bond diagram. So when the tension member P, the tension P applied to the member, and each of the hole gonna resist a pull this way, and the hole, the bolt's gonna be against, right? So gonna be against it, and then it's gonna resist. So this is gonna resist 6/1/6 of P. So each of them gonna resist 1/6 of a P. All right, right. However, if it's fractured along the path like this, so let's take it out. Okay, so let's separate the right portion. So say okay, so if we separate that, so from that we will see only 1, 2, 3, 4, 5. Only 5 out of 6 are resisting. So 5 of 6 are resisting. So that means 1, 2, 3, 1, 2, 3, 4. Oh, sorry. 4 out of 5. 4 out of 5 holes are resisting. So that means your means 4/5 P will be greater. Vn will be equal to AU. Oh, sorry, AN times FU. AN times FU. Okay, and rearrange that. Your PN will be equal to 5/4 AN AU FU. So this is your equivalent. So 5/4 is your equivalent net area. Okay, so AN, so in this, along this path, your AN will be the same. So in this case, your AN would be equal to, still gonna be equal to 5.75 inch squared, because along the path you still have 3 holes and 2 zigzag paths, so AN gonna be equal to the same, but your equivalent is 5/4. So your equivalent, equivalent net area should be 5/4 times 5.75, which obviously gonna be greater than that. So it will not be controlling. Okay, so this will not be controlling. All right. So then we can draw the conclusion the pattern 2 will be controlling, so that governs. Okay, and then we figure out the AN, and we figure out okay, so go back. In this case, we only check the two limit states, yield and fracture, right? So yield phi pn. So for yielding, remember this phi is equal to 0.9 and times Ag times Fy, right? And then we calculated that Ag is 7.5 inch squared. And what material do we use? Okay, so we use A36 steel. So A36 means the yield stress is 36, and its ultimate stress is 58. And that way, you can pause this video, calculate it, and then compare your result with mine. I got 243 kips. Okay, and fracture on net section. In this, the equation for that phi pn is this phi gonna be different. Okay, it's 0.75 times your AE times FU. All right, and this AE equals U times AN. Okay, so because this is the single plate, means that you only have one element. So in this case, your U is equal to 1. So your AE is equal to AN. Okay, so we plug that in and we figure out that your critical AN is 6 inch squared and times FU 58 KSI. Okay, and I get 250 kips. Okay, and compare, we'll see yielding is more critical. Yielding is critical, right? Then if we just compare that, yielding controls. Okay, so here the ultimate VPN is equal to 243 kips. Okay, remember that we have to check block shear and the bearing and the tail out later. We haven't covered it yet. Okay, so we can stop here and I'll see you in next video, right? Thank you so much.